ちょっとこうやって新しいステージふうに思っちゃうかもしれない。
Just mic. はい。So maybe just waiting for another 1 minutes to let everybody join us. Hey, morning. I think maybe we can start. Skip. Skip. Can we start? Anyway, so my name is Shao Wen. I'm a chief architect for Juniper Impact here. So today my topic will be routing to SDN. You know, everybody talk about SDN. It's all about the SDN controller. But really, if you really want to change and transform your network, you will start somewhere small. Then I can show you from routing protocol point of view how the industry evolved and so on. So the slides contain a lot of information from OTT networks. So I will first introduce the Google, Facebook, some information. A lot of information is actually coming from internet, YouTube, sitcom, white paper, GitHub, all the open source and so on. So, so the agenda here is first one, I will show you SDN is real. And this SDN is really impact everybody's life already. I mean, for the service provider, maybe still take time to take SDN. All the OTT guys is already deployed SDN for years. Then they actually dramatically change our networking and so on. So I will first introduce routing in Google and Facebook, FirePass, and OpenR. Then later I will show you if you build a brand new data center, which is a factory cloud architecture. So IGP, BGP not so good in that topology. So how can you kind of routing in the factory here? So later I will introduce the cloud SDN controller. So which is something we can connect all the virtual machines. So this cloud SDN controller will not try to operate on the router switch and security equipment. Will be talking to your virtual router and Docker containers. How can you see so here? So if you look at actually I will first starting from OTT networks, the fiber networks across Pacific, across the worldwide here. You can see 2018, Microsoft will build another one from US to APAC here. Google already have one. Then Facebook and Google share one, the new one. Then Facebook have something. So if you look at all the fibers, the submarine fibers somehow, you can see that's the internet we all familiar with. But there's actually private internet. Private internet built by those guys. Worldwide reachability and change everybody's life. So which is already SDN enabled. So I can show you some, if you look at this is the typical OTT network architecture. Then you can see this one is really internet, subscriber users here. Only this part is internet. That public facing backbone is private internet here. Then the data center interconnection with fibers or IP optical equipment, which is also a private internet. So internet is very difficult for you to use SDN. But all the private internet here, the peering part, all those DCI, all the software-defined data center, software-defined one networks here, is already SDN enabled. So that means your internet still, the ISP, all the service provider, this part of networks maybe take time for SDN to evolve. But the whole network here is already SDN enabled. I can show you one OTT networks. This is from YouTube here. you can see they actually innovate from 2006 till 2017. There's several software-defined controller. So from one of the big OTT, a very successful SDN deploy network here. So you can see there's not one single SDN controller can control the networks. In this network, there's 4 different SDN controllers, each working on different domain, and we will provide a different function here. So if you look at the global caching from 2006, that is a market for the global load balancer here. This one is actually software-defined load balancer. Then the B4 software-defined one networks. The Jupyter is software-defined vCenter. Then the Android controller software-defined virtualization. Then the last one is software-defined edge peering part, as mentioned. So I want to show you the OTT networks and SDN is happening. And these OTT networks really can change a lot of peering behavior, can change a lot of things. So if I ask you, I have one customer here, and I have another customer here, across Pacific, across different countries, how can I make end-to-end guarantee the SLA, like bandwidth, latency, and so on? How can I make sure? There's no way. From Kathmandu here, maybe connect to Hong Kong, maybe connect to Japan, maybe connect to San Francisco somehow. Or announce this Google Direct Connect. So the network from one user to another user will not go public internet. They will leverage their own SDN networks to guarantee the bandwidth and so on. So every user from Google GCP, if they pay a little bit more money, then they can get this load balancer function. HTTP. I can show you some example later. And this SDN is impacting everybody's life already. And they will change a lot of business decisions somehow. So eventually, all those Google, Facebook maybe become a bigger service provider, bigger than anybody, AT&T, China Telecom, and so on. So because they have a worldwide reachability, then they have SDN enabled for their networks to show all those functions here. So I just want to show you there's a lot of noise on SDN. But if you really look at the SDN, OpenFlow, or NetCom, that's just the tools here. What problem you try to solve? So we actually classify the SDN controller by 3 different categories. If you look at one focus underlay, which means you have 100 routers. You maybe use PSAC, BTTLS, BTPLU, SEC routing, SRv6, R3BT tunnel. Try to set up a tunnel from one end to another. You have a central view of this one. But that one is only for one wide array networks here. So there's options from Northstar, OpenDaylight, ONOS, and so on. So basically, this is a controller talking to the router. If you look at the next category here, you may heard about the Cisco APIC, the application-centric, very fascinating. But if you get rid of all the fancy words, what exactly the APIC does? From one data center top switch, set up another VXLAN tunnel to another top switch. That's it. So the APIC thing from Cisco is nothing new. It's just a set up tunnel from one switch to another. So Also, Contra from Juniper will also have this function. But this time we not use the VSNAT VTAP tunnel creation. We use EVPN as a central controller, not reflector, then we can provisioning all the tau switch and slide switch and so on. There's others OpenFlow-based switch. It's happening in the switch domain, in the data center. OpenFlow is okay, but if you really want to control the wide networks with OpenFlow, there's a lot of problems here. But most important things, router switch, like Southern switch somehow, that's not that's a very technical hybrid SDN and so on. But a lot of SDN controller, like a Contra, Mirage, and VMware, this time they are not talking to any physical router or physical switch. They're actually talking to the virtual router. So if you look at the Contra, you have a very big data center, like tens of thousands of servers. On every server, we created this virtual router. And all the virtual router connect back to the controller, like a EVPN. Then this time, it's virtual router. You can connect to virtual machine, Dockers, all those virtual entity here. So basically, no matter what kind of SDN controller you want to use, it's basically three categories: router, switch, virtual router. So let me first introduce the very famous SDN controller, the Google B4 One network here. So everybody know from 2011 or 2012 somehow, Google announced this one. So they mentioned they have a 12 site worldwide. And every site they have a multiple 10G, 40 giga at that time. Right now it's a multiple 100 giga bundled together. On every link, they can achieve like 98% of link usage. That means if you look at all the service provider as peering router, the link usage previously just 30%, 40%. After you finish over 50%, you can kind of increase that one. So all this information, if you look at this one, so Google designed this B4 SDN controller, centralized the TE servers, and they have gateway here. They actually use multiple server to config to monitor this OpenFlow agency on the switch. If you look at Google white paper, they mentioned Jupyter has 4 RU boxes here, 4 chips. And every chip is like a lot of 40 giga here. So multiple switch, like one rack. Then they put the routing function, the hookah, on the key agent somehow outside of the boxes. That means that they have a multiple tau switch, but 4 RU tau switch, not 1 RU tau switch. Then they group together, working as one single router here. So they're still running the SS and the BGP function with another set. So all the data center here. So Google, if you look at the Google innovation here, we are not only talking about the different SDN controller, we are talking about the application level, quick. And the TCP DDR is 2014, 2016 sometime. The gRPC is for telemetry. Then quick to replace the UDP. And the TCP DDR replace the TCP part. So one of my customers in China, they actually named China YouTube. They also support the quick. What does quick do? If you look at every phone, you install the YouTube application. Every Chrome browser support Quick already. And because Quick is open source, so some Chinese wonder like ITE, they also deploy QUIC in their networks. It's happening this year. So that means from Google point of view, the traffic, if you look at the traffic linear from one data center, one server somehow, the control is very specific. They control every flow from every user. So Facebook and Google take a totally different measure. Facebook is more like a service provider to control aggregate information. But Google here, from one data center, because they have, from server point of view, they actually control every quick plan, how much traffic you can send, and how much traffic you can get into the network and so on. So they have a very strong traffic linear networks, but they never deploy RCPTV. This one is never IP RCPTV or MPLS network from before network here. Everything is very simple. They control application, that aggregate together, then they can control how much traffic is sending to this path. But they monitor every flow. So Google mentioned, right now the QUIC is already 35% of Google's traffic. 7% of the internet traffic is running on QUIC. So if you have QUIC, you can control how much traffic to send in from one server to another client and so on. So you actually did this one. So with this QUIC and also a lot of switch in between. So Google actually defined this new routing protocol, so-called FirePass. If you look at the Google white paper, they have a FirePass. So the CBR switch and non-CBR fabric switch is no BGP function. This one has BGP function. This one, they have a multi-port Tor switch in their networks. The Tor switch will sending the information, connect the information sent to the controller. So that means every router, every switch in Google networks, they actually send those information back to this FirePass master. They have a multiple server to get the network topology information, to get the BGP information, and so on. So they modified ISS networks. So the Google first SDN 10, they start from a customized ISS. So all the information will send to this server, and the server will calculate the path and send to the leaf and span, and distribute the SPF calculation and so on. So they define FirePass master redundancy protocol. They define the link state database EBGP protocol and so on. So instead of every Tor switch running ISS as a single router, so they actually the whole network just running one ISS, but they have a redundancy protection. So the whole network from Google is actually open flow, the ACL table, plus the IGP calculation, longest prefix IGP. So if you look at one server to another server, how much traffic you can send. So Google, because they changed the FirePass routing protocol, so they can set up two different equivalent paths. One is from this one, another from this one, based on the IGP calculation, and also based on those open flow access lists here. So they make this path and this path equivalent, so they can load sharing between the two paths. So in that case, if you look at this one, so I can, because a lot of data center traffic, if you go back here, the data center traffic and the data center goes to the peering, it goes to the user. Majority of the traffic from one data center to another is 95% of the overall traffic. Only 5% goes to the user. So from my home, Singapore, I got 1 giga connection. Every day I can do like watch a lot of YouTube, a lot of knowledge shared on YouTube. You think YouTube traffic, then a lot of customer, every customer got 1 giga connection, the bandwidth is very big, but not true. From one data center to another, and from data center to the user, machine to the user part, is only 5% of the overall traffic. From one data center to another data center, it's 95%, like 20 times bigger than the overall YouTube traffic goes to your home somehow. So how can you control those ones? It's based on this FirePass and based on this OpenFlow part. So they use very simple switch together with ISS, together with OpenFlow, they can control all the traffic. So let me show you another example, like Google totally changed your network. So this is the solution we built for our customer. Juniper is part of this solution. This solution is not only for Google and Facebook, other customers also benefit from this one. So we built this solution in 2016, 2015. All the Juniper routers can support this one already. So the benefit for this one is, if you look at the traffic engineer inside the ITP domain, which is everybody can do, but it's not relevant to a lot of use cases. So from traffic engineer point of view, ITP-based traffic engineer, not so important. BGP-based traffic engineer, getting more attention here. So how can you control the traffic and connect to a different peer, connect to different OT cloud, and to avoid any congestion here? So Juniper proposed an AKF draft. We assign different label for different peering. So for this one, if you sending traffic from here, then you try to avoid the congestion here. For example, this link, all these peers are already congested here. So in that case, you can just changing the inner label. You push different label, then this router will follow forward to different peer router here. Very simple. And in that case, you can do two things. First one, find out which peer router not congested. The second one is finding which, first one finding ASDR. The second one finding the peer router. So they push two different labels, like second logic somehow. Then you can get all the benefit here. I just briefly introduced this technology here. But actually, Google published some white paper, leverage Juniper solution. So from April 2017, so Google released the fourth pillar for OSD controller. The first one, Jupyter, is a software-defined data center. Before software-defined web networks, Android controller, software-defined cloud virtualization here. Then the last one is Espresso, the software-defined peering part. So the whole idea is based on this solution. So we co-work together with our customers. So if you look at this one, so like I mentioned, so from our data center, which is a green box here, a blue box here, blue circle here. So this one is all the Google equipment here. So but all the green boxes here is Wonder boxes, or Juniper PTX display a KO here. So every day you watch YouTube, you must pass certain of a Juniper peering router already. So the things here is the user watching like a high quality video from YouTube, but somehow this link congested. So the server from a controller from Google will automatically switch to another path to reach to the customer. how can they do so? It's actually from an application here, the host, from server, from Google server, they send you traffic. So previously, they can send a lot of traffic. But right now, if the traffic not so congested somehow, then they will feed this application signal here. Then there's a application signal, which is from Quick. You remember that every YouTube application is used. So Google have some method to control the every Chrome browser, laptop, and mobile phone, and on this one. So they will send this application signal to the global controller. So the global controller will find the local controller, then they will find which BTP speaker and which PTX box here, then sending the traffic to different here. So that's a solution. So the idea here is this link congested. So the controller, the application will notify the controller. Controller will find another way of sending the traffic here. So Google mentioned this Espresso controller already deployed in Google for past 2 or 3 years. And 20% of YouTube traffic already controlled, optimized by this controller. That means every 5 times you watch YouTube video, that's 1 time this Espresso controller already kicking and help you to find a better source, better caching function as well. So I briefly introduced Google's SDN network somehow. Later, next session, I will introduce Facebook OpenR. Why Facebook defined a new routing protocol? What happened to our currently routing protocol, OSPF, ISS? What's the problem? So if you look at the routing method here, it's actually distance vector, link state, path vector. So on the forwarding table, every router forwarding table, they actually don't have a whole picture. Every forwarding table on the router is same like a sandbar. They will show you to Las Vegas this path, to San Francisco another path, but they don't have a whole picture. So if you look at try to reach from Summerside to San Francisco, you actually try to calculate a path. Then this path vector, like BTP part, will kick in, will help you. So like a distance vector is read, link state OSPF ISS. The path vector is like BTP. So from a data center network design point of view, a lot of people are thinking, oh, IDP too much flooding. IDP not so good. OSPF ISS not so good. BTP will be the clear choice. But BTP is actually not calculating anything. So it just show you from one AS to another AS, how can you reach it. So really, which net hop, which interface, and so on, is calculated by this link state here. So let me show you the very old protocol. I've been working on the OSPF and BTP for 20 years. I was coder developer for OSPF and BTP. So if you look at the packet capture for BTP, they actually use the TCP port 179. Then there's lots of information here. If you look at the OSPF, even worse. They actually define their own IP port number, not TCP, not UDP. They define the port number, they will send a lot of information. So bits and bytes. So a lot of people are thinking about if you really know the OSPF BTP, you must know the bits and bytes. So that's a bits and bytes, a lot of detailed information. But modern technologies, modern routing protocol, like Rift from Juniper, routing in the factory, I will introduce later, and OpenR, they will not build their routing protocol by define an IP protocol port number, by define all the message format and so on. So if you look at here, the protocol message from OSPF, a lot of protocol message. Then even you try to set up a neighbor adjacency for OSPF. The star attack initial two-way exchange star somehow loading. Take time to set up the neighbor. Then you have a lot of different, all kinds of LSA. LSA 1 to 9 somehow. So, but if you really look at the routing protocol, or even any map, Google Map, and it is from one end to another, and you have a different cost based on latency metric and so on. So you actually draw this picture, then you do the shortest path, you attach the shortest path one by one, then you send to the destination, then you can calculate which way is the shortest path. So that will not change. So even all the new routing protocol like WIF and the OpenR will not change that part. But they actually can change a lot. Let me show you OpenR from very beginning. So OpenR can run in the Facebook OS, Arista US, and Juniper Junos Linux as well. So this is public information already announced. So OpenR try to solve the data center scenario. So like a 5-stage class architecture, like a 4 different span plan here. Then you have a lot of edge switch and rack switch and so on in like a wedge and backpack, all those architecture. So OpenR try to define to use in the modern data center networks. That's the first attempt. But so far I heard not so great in that one. Then the next one might be successful is the new backbone network from Facebook. So OpenR can run it on Juniper MX PTX from 18.1 from this year, March, April timeframe. Then you have I think in total you have a BGP injector somehow in between here. So let me show you. Let me show you why they use the OpenR instead of the normal common routing protocol. First things, the Facebook actually use SD controller. And all the SD controller talking to all the routing protocol here to get the information, OpenR information. Then they have the NetFlow collector. So like I mentioned, the Facebook can take a very different way to control the traffic flow other than Google. Google's per flow, per application control. So Facebook is more like a per prefix and per destination somehow. They enable NetFlow everywhere. Then they actually use BGP injector to mapping the prefixes to different destinations somehow. So this is the brand new backbone network from Facebook. It's very different from SP network design. First of all, they use a 4-way active-active redundancy. So 4 different plans. So connected, if you go back here, the data center switch is 4-span plan here. And also from data center to the one network here is all 4 different 4-way. So they can do A/B testing. So they mentioned the OpenR is so good. So they can define any protocol, any message in minutes. And they actually deploy some new features every week. Every week, the OpenR protocol like change like 20 times now. So a lot of change on that one. So let me show you how far can you go? You can go. If you use the modern technologies here, then you can go really far. If you use legacy method, not so far. So the hidden technologies behind this OpenR and Rift is really message bus, 0MQ, and in-memory distributed database. Two important tools for you to design and build a new routing protocol. So why I need a message bus? Because all those information sent to the controller, sent to the router part, you don't need to worry. You just pop and stop this message bus, then every router can know each other. So for the in-memory database here, also very simple. So you do not need to worry about sending information from this router to another router, and to make sure the sequencing, all those kind of authenticate all those information. You can just use a local RAID, commit it into the local RAID. Then this KB stop will automatically sync up with each other like a peer-to-peer network. So this is the OpenR architecture here. So if you look at the OpenR, why I list this shift very important here. So the OpenR routing protocol, when they put up, they will not construct a lot of message, like a protocol discovery, all those things. These two routers put up, they will pick the IPv6 link local address to discover each other. And then they start this Swift server. They start this Swift server, then we can exchange the database immediately. So all those kind of protocol message, existence state, LSA, maybe not request here. So if you look at OpenR here, they have a prefix manager here. They have a KB store like a database exchanging each other. So the two routers, they put up each other, then they use link monitor. The Spark is like a BFD or the hello packet to detect the liveness here. Then they will sync up each other, sync up on the KB store database. So all the link state database will automatically put up and sync up each other. Then they will make the decision, create a forwarding table, and send to the hardware platform here. So very simple. Instead of you define a lot of protocol message, so the whole idea for Rift, for OpenR is two databases sync up each other. So that's some more information you can mention. So I just want to show you the OpenR is already running on top of Junos. We published the news together with Facebook. So either way, you can run the legacy, previously all the ITG, BGP in Junos, or you can use OpenR. But OpenR, like I mentioned, is just the ITP protocol. It's not a BGP protocol. You still need BGP, stack routing, you still need others protocol information. So the OpenR will generate this RAID API and through the RPD. Because of very beginning, we actually working together with Facebook. We try to like OpenR to kind of modify the forwarding table, but that's not a good idea because for the ECMP, for the load balance and so on, so that's really not a good idea. So in that case, you have OpenR, you have RPD, then you can passing all the message to the Juniper boxes already. So we open up all the RAID update information API to other projects. This one is not only for Facebook, but Juniper, all the routing protocol, Jack, Juniper is in 2K, is open to all the customers. So I kind of discuss on the normal ITP protocol and the modern routing protocol for the SDN part. I will discuss a little bit on the routing in the factory which is inside data center. How can you build a better protocol here? So if you look at the routing protocol, OSPF, NSS, BGP, they can fit for any topology. That means they are not optimized for any type of topology. So any hub and spoke, all those ring topology, all the routing protocol can handle. But if you look at the data center networks, like a multiple stage factory, cloud architecture, fold factory somehow, tall switch, aggregation, span, and so on. So none of the routing protocol actually optimized for factory yet. So ITP, BGP, they all have a lot of problems. So there's some attempt try to optimize the protocol by introduce actually two drafts, try to modify the ISS for this data center network. The first one is from Xiaohu. He joined Alibaba recently, and myself here. We actually proposed flood reduction in the MSDC. So if you kind of get rid of the flood reduction, then this ISS can do much better job. Another guy is Tony Lee. January, like 1 month ago, he actually published a new draft to optimize the ISS dynamic flooding for ISS. So there's several ways to do so, but that's kind of a patching on the existing protocol. So if you look at the data center networks requirement, so they actually define the data center networks requirement by RC 7938 here. So they define a minimal OPEX fabric. So there's multiple different ways to do so. So first of all, you may modify BGP for certain case. And then you may modify ISS for certain case. But the Juniper actually proposed this RIFT, routing in the factory. The new IETF working group is dedicated for this data center network here. You can solve a lot of problems. Let me show you some of the key idea for this RIFT protocol here. First of all, they actually define the network have a direction. West and east and south and west, south and north here. They use the link state flooding up. They use distant vector dot. That means half those topology is actually ISS. Another half is actually RIP. Why I need a distant vector to send those information back? Because if you look at the data center networks, a lot of tall switch, this tall switch for the table is very small, less than 128K. But if you look at all the span switch, especially from Juniper, which has about 2 million, 4 million for the table. So if your network grow very big here, so you may need to send in the default route to this level 1 and the level 0 here. So you define different level 1, 0, 1, 2, then you confine the flooding. So all the level 2 information sent to level 1 will be only default route. The level 1 sent to level 0 also default route. So then they also define this one layer mask. I can show you why we need this one. So the idea here is you can define different pod and different level. And you will automatically reject any adjacency here. You will automatically take information within levels. Then protocol works as if level 0 allowed to connect to level 2, but the optimized routing will need a very large for the table underneath. So this new routing protocol fixes all the problems. Smaller for the table on the call switch, and automatically get cabling and minimal topology change somehow. So all the topology change will be confined in this pod, will not extend into another pod. So we do a lot of aggregation in between. So let me show you this switch connect to one of the virtual router or so virtual machine or Dockers here. The prefixes is maybe prefix 1. So this information will be sending up, like just a normal NSS OSPF sending up. Then this router and this router will receive both those information. You will send default route to this one. So if you really want to send traffic to P1, you just send traffic to me and to this one. But if this link goes down, for example, this link goes down, so the information sent to here will not be kicked in here. So the information you send the traffic to here will not reach to P1. So how can you fix this problem? We actually define this bounce. So the information sending from one span will be automatically bounced to another span. The database will compare each other. So if you see that this router's database will not contain the P1 prefix 1, so you will automatically sending the more detailed P1 prefixes to this yellow router. And this P1 will send it to this top switch instead of the default route. So on the top switch, very stable environment, you only have a default route. Then you can send traffic to update. But if something goes down and some topology change here, you will have the more detailed prefixes here. So in that case, it will follow forward traffic to here, not here. So we define different level. We define one level fast. So that's the idea. So if you look at the advantage of this IP fabric somehow, they actually combine the advantage of the link state and the distant vector, the fastest possible convergence here. So convergence is really, really quick for thousands of routers. It's within several milliseconds somehow. Then automatically detect the topology change. The minimum mode routing on the top switch. The higher degree of ECMP can support 128 and 256 ECMP. Then a lot of advantage on the reduced flooding, and all the top switch here will be zero-touch provisioning. So in that case, you do not need to configure anything on the top switch. It will automatically connect to this application switch and the switch. So zero-touch provisioning is another feature we actually work on this one. So let me show you. This is a laptop. If you look at the Rift protocol design, all the interface, all the topology is defined by YAML file. That means you can define any new message protocol. Just like previously I mentioned, OpenR use a fixed object to define the protocol message somehow. It's not really dedicated protocol information. So all those kind of YAML file, all those you can run different desktop distance interface somehow. On my MacBook Pro, I installed the Rift protocol in my laptop already. So we can simulate like a 21 node, 16 links, 600 prefixes here. We can achieve faster convergence like 300 milliseconds. Then we can single link flagging a super span and 2 times faster than any IGP. Then we can achieve a 15 millisecond convergence time for any link convergence. So eventually, this is the Juniper LAN card. This is the RE control plane. We have a BGP stack locking, the OpenR Rift, and SD controller could be any of a new protocol on top of our process. So the idea here is we actually use exactly the similar way on OpenR. So we use KV-stop, we use the message bus to exchange information between routers. We use KV-stop for those in-memory database for the database synchronization. So that's pretty much for the routing protocol part. So the last topic I will share is cloud SD. Cloud SD controller. So if you look at the data center networks, you may use like a fusion, like a router and a switch somehow connect together, and will automatically become one. The VCF, the traditional layer 2 multi-channel LAN somehow. And you can also use IP fabric. You can use BGP Rift or even OpenR for IP fabric. So to get the connectivity on the IP fabric. Then another part is the EVP, VXLAN, and MPLS overlay, the control SD controller. So before I talk to Juniper Cloud SD controller, let me show you the Google data center controller, virtualized physical network controller. So Android controller is one of the virtualization in Google. So why this one important? So Google networks, they have a lot of containers. So the container networks are on every server, so like 10,000 server plus. So the container come and go, and then they will create a new container and they will destroy new container. So Google mentioned in their network, in their data center network, every week they will create 20 billion containers in their networks. And every week they will destroy these 20 billion containers. Every container will have an IP address, and will have any policy, DNS, and so on. So in that case, imagine how big this network will be. So this time it's not a physical router, physical switch. It's virtual router. On every switch, which can connect multiple Docker containers. So Google actually created this Android controller, the so-called host virtual machine management somehow. You have a multiple virtual machine or Dockers here. And then every virtual machine Dockers will assign the IP addresses, will be config all the log balance, DDoS, ACL, VPN function. If you look deep inside it, this virtual machine, from a virtual machine transmission, then you can go through a firewall security. Then you can go through the rate limit here. You can go through the billing system here. Then you can do the in-cab, and you can do the routing and send traffic out. From one virtual machine or Dockers, connect to another Dockers here. So Google actually used the overlay method. So that means it's IP in IP. So you have every server, you have a public IP addresses. The every virtual machine or Dockers, you have a private IP addresses. So you actually sending traffic through this server. Then you put the public outer header, public IP addresses here. Then they will automatically create a lot of tunnel. Then send it to the egress router here. Then it will decap and get all this information back. So if you look at the Google Android controller, they can not only can talking to the software switch, but also fabric switch and packet processor and cluster router all can connect to the Android controller. So, but the idea here is IP ENIP overlay technologies. So let me show you how Juniper Control can do similar job. So imagine you have one very big data center. you actually create a lot of virtual machine Dockers and so on. So on every server, you may have a multiple virtual machine, you may have a multiple Dockers here. And on every server, after you install Contra, then Juniper will turn this server into the virtual router here. This virtual router will have a multiple interface connect to this virtual machine. Then if this one, you use OpenStack or any cloud environment to create this Dockers containers here, you click the button, create this virtual machine Dockers. Then this one will attach to the virtual router. The virtual router will gather all this information, sending the traffic, sending information to the controller. So the virtual router will not talking directly to another virtual router because of we are talking about tens of thousands PE. If you fully mesh a lot of PE function, that protocol overhead is too big. So we simplify the communication channel. Every virtual router will only talk to the controller. So to the controller, every virtual router like a virtual LAN card. So everything will centralize and send to the control controller. Then they will calculate the path. If, for example, if this Docker's virtual machine try to talk to this one, they will put the tunnel in between automatically. So in that case, you create this virtual machine, give the IP address like 10.10. Then this IP addresses will automatically send to the controller. Then another 20.20 will be automatically can exchange information already inside one data center. Then outside network here, the 10.10 maybe private IP addresses will be do the NAC translation and sending to the BGP gateway router on the data center gateway router. So we will automatically, so you click the button, wait for one minute for this Docker or virtual machine to bring up. Then the rest of the network can already utilize this resource. So that's the beauty for this Contra SD controller. If you look at the Contra SD controller, this one looks like the control plane. Then in the middle, IP fabric or the cloud fabric, like a virtual fabric. Then every Contra switch and third-party switch looks like the virtual LAN card here. So in summary, if you deploy the Contra in one data center, the whole data center becomes one big router. So they will connect everything together. So you will not need to deploy anything. The policy, all the service chaining, everything will be automatically managed by the Contra controller. So in summary, this is the new SD controller, which is quite different with OpenDLI or ONOS. Why? Because of OpenDLI and ONOS controller, it's like they have arms to control the router, but they don't have a brain. Why I'm talking about the brain? Because of all the virtual router here is actually sending the information like a virtual RR. So this dot reflector, this controller will notice any new node adding to the network here. So Contra SD controller like a Nuage and VMware, they have one brain. So the OpenDLI, ONOS, like just R, they don't have a brain at all. So the data plan, they can do whatever for GRE, UDP, and VSLAN. The control plan, they use BGP. Then they use SMTP. Then they actually working as one single brain. So from a controller point of view, if you look at the draft from Juniper, as a so-called layer 3 native AND system here. So the controller here, the controller will sending the SMTP message, not the BGP message. Why? Because the BGP message is a lot of overhead here, not so good. So we actually can see that IP addresses and then the tunnel encapsulation and next all those information like just like a BGP information sending from controller to the VPN forwarder, the AND system, which you are. So the idea here is COM12 SD controller. You have one virtual machine, you have another virtual machine on top. You have two different computing systems here. Then they will send in those you create these IP addresses, they will gather those information sent to the control node. Then the control node will automatically programming this another forwarder by SMTP. So by the message I showed you before. This is SMTP message I actually take from real networking. So the two server can connect, they have a physical public IP addresses. Then there's a virtual machine, like a private IP addresses connect to this server, then connect to this VRF. Then first one is this virtual machine, then those information will send to here, then it will program like a 1.1 next hop is this server, then label is 39 label. We create a label for that one. So in the meantime, if you create another virtual machine on the computing node 2 here, those information will automatically to the control node and sending to 10.1.1.2. Next hop is like this server. The label is 17. So in that case, you create this from 111 sending to traffic to 112 here. Then you send it originally payload here. Then you adding the GRE label or the GRE or the MPLS somehow. Then you adding the label 17 here. So this is label 17 here. So public IP addresses like public IP, then GRE label, then it's private IP addresses. So if you look at the COM12 nesting controller, so-called nesting controller, but really this is the EVPN end-to-end EVPN simulator somehow. So from one data center, you connect to another data center. It's a protocol construct SD. So that's a message. But if you look at the modern SD controller like a COM12, again, share the same architecture as OpenR and RIP. So the internal architecture for COM12, they will use RabbitMQ message bus. Then they will use Cassandra database and use Zookeeper for sync state here. So basically, this database and the message bus is very important. If you look at all the modern routing protocol, all the modern SD controller, they actually share the same architecture, same component building block. So with all the like a Swift server, all the database, all those kind of message bus, somehow you can build a better controls. You can also build a better SD controller here. So just in summary, this is Google's fall SD controller. Data center one, Jupyter data center, the fabric controller. So how can you connect the multiple switch together? That's a Jupyter fabric controller. This is Andromeda controller like a virtual machine somehow. So I forgot to mention that. Let me show you this Andromeda controller. Andromeda controller is just you have a public, you have different IP addresses for server. Then on that one, you have this virtual networks. This red one may be for YouTube. Orange one may be for Gmail and for other services somehow. So basically, on the Andromeda controller, it's use overlay technology, IP. You put all those private IP addresses information into this tunnel. Is exactly the same as COM12 SD controller. But this one is very important for any Docker containers, so-called cloud SD controller. Without this one, so like I mentioned, only Juniper, Nokia, and Cisco, not Cisco don't have, and they have also cloud SD controller, which virtualize the software virtual router. So So this is Android controller. So based on the server, you create a virtual networks and use overlay technologies. The Jupyter Fabric controller, then the default controller, like I mentioned, they have a multiple tall switch, like a 510 tall switch. They actually use an external server running the FirePass. FirePass is very old routing protocol for Google. They actually get rid of this FirePass 5 years ago. The new routing protocol is more like SDN method. But you can see the default SDN controller, which is can control the data center traffic to another data center traffic here. So 1, 2, 3, and 4. From the server, then you can all the way connect to the Wander router, like a Google Juniper router PTX. So from here down, all the physical boxes are from Google switch. It's actually one single switch. Switch can be used for 9-stage clouds in this one. If we have more time, we can introduce Google inside this center. Then this similar tall switch will be running on the default router here. But all those other boxes, the majority of the boxes actually coming from Juniper as peering power. So if you look at the default controller, we have a Juniper, we have a Northstar SDN controller, which is we cannot control every application like a Quick and TCP DBR, but we do aggregation. We do per LSP monitor on this one. So Northstar, we can simulate the default controller function. Then for the Fabric controller, we have a Contrail. Previously, Contrail only working on the virtual router. But this year, we actually bring the Contrail to control the deep and span switch. So this deep and span switch, Contrail can do so. Network Director already can support the EVP baseline with Ansible, all those modern scripting. We can support a very large scale BTP-based fabric. Then Northstar will help you to simulate the function for the ES. So if you look at really one big SDN networks, you have a different SDN controller to working on different things. So even Google actually open source all those SDN controller because your application is not the same as Google. You cannot leverage all the benefit from Google. So you must working with one vendor, which have this virtualization controller, cloud controller, which have this one SDN controller with peering controller, network director somehow. So Juniper is a trusted one which with all the OTT guys for years. Then we actually building a similar SDN capability which can help our customers. So I will wrap up by this all self-driven networks. So when I joined Juniper like 3-4 years ago, before that one, 2011, 2010, I was a product manager for another one. I think I know all the products, IGP, BGP, all the tunnels, GRE, VXLAN, everything. So there's nothing in the network. But the whole SDN introduced in 2011, 2012. Now all those telemetry, all those network self-driven, the machine learning, all those intent-based networks really changed the network dramatically. So we are talking about even all the SDN controller is like a machine controlled by the user, but eventually will become a machine controlled by another machine. So for example, if you this is like a network here, you not only can control the network here, that's easy, but how can you make sure when you change the LAN, there's no damage for others. So for example, you must know all the information surrounding you on the network part. So I always give the example here. If I'm driving a car, so the self-driven car, I will not only to measure the distance between the cars, and also measure this car's speed somehow. And if I got more information, like this driver is like a lady driver, it's not so fast, it's not willing to kind of cut queue somehow, so I can safely to turn from this lane to another. But this guy, I cannot second to nine, so I must be fast one, so this change lane will be very dangerous. So all those telemetry and big data analytic part really change the network. So like creating from Juniper CTO mentioned, we are building to close the range, close the loop. So first of all, your network, you must have an SD controller. You must think about the SD controller from now. SD controller is not some fancy word like from very beginning. It's already impact. Every day you watch YouTube, already SD controller taking care of certain function. Then this SD controller will automatically to control your networks. Then you use OpenConfig and Google Protocol to get all those information. Then you apply the big data machine learning to better to monitor the network. Then you close this ring. So eventually, we believe that machine control machine or machine manage the network that will be will happening in the next 5 to 10 years. So that's all for my session. Any questions? Any comments? We still have around 10, 20 minutes somehow. Okay. So because actually this session we introduced a lot of new technologies, like Rift, OpenR, and Control SD controller. So feel free to reach out to me offline, and if you have more questions, and so on. So. Which one? Is Jim Lindenroth? Meaning, oh, okay. So from a SD controller point of view, yeah, actually we're working with a lot of customers. Very beginning, everybody wants to free lunch. They want open source. Then Open Daylight, all those. But right now, the Open Daylight, a lot of vendors actually not take very active in those. So very beginning, different vendor, open source one, the quality not so good. If you have some problem, nobody help you to fix that problem. So eventually, if you go with the open source, even when you have a very strong technical team in your company, otherwise will be really, really difficult. I mean, for the SDN part, if you talk about this, if you look at this cloud, clearly like a virtual router here. Nuage and the VMware is actually the controller control the OVS, open vSwitch switch. So Juniper actually control the virtual router. The node switch and the router, they have different function. They cannot interop with each other. So part can be control, certain part can be VMware, that's okay. But if you look at this part, the controller, if you buy from a Juniper, Northstar controller for the outer part. You can actually talk into any Cisco Nokia boxes. The controller, you must have one single unique one, but the box, which is more important and more expensive, will be installed together. So if you look at the Open Daylight ONOS, Northstar, we actually have a lot of new functions, like SRv6 eventually. We have a different function here. So, but if you look at the Open Daylight, if you take SD controller like Open Daylight, you only use OpenFlow. Then OpenFlow working with any other process. But in that case, it's actually not so good. So there's pros and cons. A lot of service provider and OTP guys try to use open source, but they actually take a lot of problems recently. I talked to certain China OTP and ISP, they all try to use Open Daylight ONOS. But so far, it still have a lot of problems here. Any more questions?